number 3. So I know it takes a bit of effort to get here, so we take a start and hopefully other people will join us. So we shift to, I'll pick up the conversation where we left off yesterday. And before I move on, are there any questions, comments, complaints, concerns about the stuff that we've discussed in the previous 2 lectures? It was really meant to give you an overview and a flavor for different types of methodologies and tools that have been developed for systems analysis, optimization, and modeling. And for those who are interested, there are lots of resources available that you can, inshallah, use to further your interest in those areas if you choose to do so. So I focused more on methodology in the first 2 lectures, and in the next 2, now we're going to talk a little bit more about applications. So, now that we have some of these frameworks and some of these approaches, what are the types of questions we can study? So, which brings me to the question of the water, energy, food nexus, which is one which is an important area, I think, for Pakistan, I think, for many regions, where we need to improve our understanding, and we're only just beginning to develop a better handle of these issues. So again, in our course roadmap, here we are on sorry, you received it? Okay, so here we are. We'll talk about water and the food nexus. So I like starting off with this picture, planet Earth, and I really like this quote. Does anybody know who Arthur C. Clarke is? So he was a visionary and a very, interesting, done a lot of interesting work. And he was the first one who came up with the idea of satellites, actually, Earth observation and communication satellites in the 1940s, way before, and some of these rockets were being built, or space travel, or even orbital satellites became a reality. He was the first one sort of proposed developing some systems. And I thought it was very apt that how inappropriate to call this planet Earth when clearly it's ocean, right? So we all know 70% of the surface is covered in water, but yet we call our planet Earth. But I think it drives home the message also very clearly that water is so intimately connected with our lives on the Earth that we live in, so intimately connected with the food that we eat, and also the fact that this planet is finite. I put this picture there to recognize that this is it. We're not getting any new water from outer space. The hydrological cycle is closed. We have the water that we have, and that's it. We have the land that we have, and that's it. So recognizing the finiteness of these resources should help us think and appreciate the fact that sooner or later we are going to run into growing interconnections and into growing constraints on how one resource would impinge the availability of the others, and so forth. So we have a population that's increasing both at the global level as well as here in our country, Pakistan. So sooner or later we are going to run into issues related to constraints because of the finiteness of the resources that we have on this finite planet. And that really is the heart of the matter when we start thinking about the interaction between these systems, and the water, energy, food nexus derives from this. So I like to, sort of begin from the beginning. Many of you are, from the water sector, and you appreciate this very well. And for many of you have read this, that human civilizations are also sometimes called hydraulic civilizations. Most of the major cities, large civilizations, really developed along riverbanks, as the Indus side the other day was also referring to this. And we need to appreciate that, some of the early structures, some of the most impressive engineering feats were related to harnessing water resources, which made large cities possible and led to the civilization, whether it's Mohenjo-daro and Harappa here in the Indus Valley in the Indian subcontinent, or whether it's Egypt or Mesopotamia or so forth. But a key thing that I want to point out is that as humans develop the techniques and the knowledge and the expertise to move water across massive land areas and and use it and supply it to different populations, they weren't using active input of energy. All of these old structures were built in which the power of gravity was harnessed. So the water would flow under the influence of gravity from one point to the next. And the whole field of civil engineering and many other areas within the water sector and the related sectors developed within the particular domain, where there was little consideration and, quite frankly, active linkages with, let's say, energy in this case, right? So they weren't using pumps, they weren't using anthropogenically derived energy. But now the modern water systems are very different, right? We are using massive amounts of energy to extract, produce, treat, distribute, use, treat, and recycle, and potentially dispose it back to the environment. We're using a lot of energy within the water cycle. I gave you a little bit of example of the urban water cycle the other day in the first lecture. That these energy inputs are not trivial anymore. And similarly in the agriculture sector, it's not just water alone. In agriculture, we've mechanized and modernized our processes. We're not using animals or other forms. We're using large-scale machinery running on diesel, electricity, and so forth. So now we're putting active energy inputs at the farm level and beyond to produce our food, to use it, to process it, to distribute it, and to store it. And then similarly in the energy sector, we're using ever more amounts of water than what was used before. So all of the shale boom in the US and many other regions for extracting shale oil and gas requires a lot of hydraulic fracturing, where they basically use massive amounts of water to fracture basically shale formations and then access some of those unconventional energy resources that previously were not being accessed. But now, as we have pushed to explore for more and more resources for energy because of the rising energy demand, we're developing all kinds of new technologies in which we're using some of the water resources or energy resources in ways that we were not doing so before. And as these technologies develop and spread at a wide scale, what we're finding is that we can no longer simply ignore that this one sector alone is what we need to focus on, but what we really should be doing and need to do is better understand how are these resources interconnected as we deploy some of these large-scale systems. Okay, so basically the main idea is that the value chains of all the processes ranging from extraction to processing to distribution to use across all of these sectors increasingly are interlinked in the water, energy, and food domains. Okay, so here are some examples. Another example for the water sector is basically desalination plants that we were talking about. They use a lot of energy. They're increasingly deployed. Of course, the largest capacities in the Middle East, but they're increasingly being built all over the world. Sooner or later, Pakistan may turn to some of that desalination. In Karachi, they had a desalination plant. I don't know how well it's functioning, but sooner or later, this is a need that is going to arise, and cities along the coast are turning to this source. Similarly for power plants, water is an important input because it's used for cooling purposes, for electricity generation, and the lack of availability of adequate water supply impacts plant efficiency. Dr. Zahar was mentioning the other day about the specific heat capacity of water. Water is an incredible solvent. It's also incredibly good at absorbing heat. So because of its high heat capacity, it is actually a very efficient working fluid, and therefore it's used in power plants to basically cool the necessary parts and improve the efficiency of energy production. So you need water to produce this electricity. Similarly, when we talk about other sectors such as biofuels, of course there hasn't been much discussion here in the context of Pakistan, but globally this is an issue. In the US, now it's a mandate that they need to mix 10% ethanol in all the gasoline that is sold in the country. All that ethanol comes from corn production, and corn production requires water. So now you have interlinkages between food, between water, and between energy. So there's all of these interactions happening, and very little is understood about the implications of some of these new technologies and approaches. Okay, so essentially this whole term, the water, energy, food nexus, that sort of emerged in the last, I would say decade or so, or maybe the last 5, 7, 8 years ago, essentially is a concept. It's a conceptual recognition of the interaction between water, energy, and food. And in one sense, it's sort of simple, of course, and straightforward. But in another way, it's actually pretty profound, because what this concept allows us to do is to appreciate that we can't just address one piece of the problem without discounting the other side. What we may end up doing actually is we may seemingly improve perhaps one problem, but what we may end up doing is creating worse situation perhaps in another area. And that's really the idea of thinking about these things in an integrated way. So there's been a lot of research and recognition of integrated water resources management. People in the water sector would know that. So integrated water resource management, in which the idea that, you know, we need to look at basin scale, we need to look at the bigger picture, and we need to really sort of not just talk about non-water, not just surface water, but really the whole. But then this is sort of really extending that idea one step further, saying that, you know, it's just not enough just talking about one domain anymore. What we really need to do is understand how it connects with some of the others. And if we do not do that, we do it at our own loss, because what we may end up doing is creating this problem. So how did this all, you know, sort of start? People have been talking about, you know, interconnection between water and energy for a long period of time. If you do a review of the literature, and if you see what's been published since the 1960s and 70s, people have been writing about, you know, the energy implications for water use and so forth. But in the last decade or so, this issue has gained a lot more attention, primarily driven by industry, actually. So what I'm showing you here is an issue map. This was developed some years back, 2007, 2008. And it reflects essentially the results of a survey that was conducted across 41 CEOs of major global energy companies. And these CEOs have gathered at Davos, Switzerland. There's the World Economic Energy Forum that is held there every year, in which essentially leaders of academia and heads of states and government and politics and industry, they all converge and they discuss critical issues related to the global economy and human welfare and so forth. So they gather and essentially identify what are the emerging threats or what are the emerging issues that people need to consider. So for the energy industry, survey was run, and they mapped these factors out in their issue map, if you will. So that's what you're seeing here. So they have all different types of factors listed here, and they're talking about politics, and they're talking about many other issues, but you can see that water is somewhere here in the green zone. So, you know, the energy CEOs, when they were polled in 2000, you know, water was that much of a concern. It was there on the map, but it wasn't much of a concern at that point. But within a very short period, so here's, I've just labeled it in red, so you can see. But the next year when the issue map was generated, you can see that the water issue had migrated up on the yellow and orange zone, indicating that they were increasingly getting nervous about the sustainability and reliability of water supplies for energy production. So these are energy company CEOs worrying about water, something that was not done in the past. Why was this happening? Why was this shift happening? Well, it was happening because a lot of real-world situations and real-world events that were unfolding. So, for instance, in 2009, France had to basically halt power generation and import electricity from the UK because of basically they had a long, prolonged heat wave, and they couldn't run the nuclear power plants because of discharging of water at a higher temperature, which was not allowed. So because of this water cooling issue, they had to shut down some of their electricity generating capacity and import it from outside. Similarly, some other plants, also in the US, they had to halt electricity production from a number of nuclear power plants because of not having sufficient water supplies flowing through. So here are situations where you built and sited power plants thinking that water was this limitless, abundantly available resource that they never have to worry about. It was not a design constraint at the time. And now you're basically coming up with this constraint, which is actively impacting your power generation. And of course, the revenues and profits for the company. So there were a lot of things happening which had raised this issue within the energy sector of recognizing that water is running into more competition, and as well as when you think about the future uncertainties, what would that imply when maybe because of climate change or changing precipitation patterns in other sectors, the domestic sector and so forth, requiring this resource ever more. So this is just an example of the growing concern that emerged, which drove some of the research and some of the activities that we now see in this area. It was really coming from practitioners and from industry recognizing that we're running into this limitation. So why were they concerned? And why do we need to care? Well, here's some data. What you see here is essentially the water intensity for fuel production across different technologies. Notice that this is a log scale, and I'll just qualitatively point out that for certain types, there's not a whole much of water consumption going on. So for natural gas, you don't need a whole lot of water for production, but certainly for oil production, you do. So this is oil production just using primary and secondary techniques, but enhanced oil recovery requires a lot more water because water is injected in the wells to increase pressure and recover more oil out. And similarly, corn ethanol that I was just mentioning, it's way out here on the map. So what this lets you appreciate is that depending on your energy policies and depending on the fuel choices you choose to go or pursue, there are major implications related to water reuse that you're also implying. So it's not just an energy question anymore. It's also water question. Here's data showing the amount of water needed for power generation, varied by technology, so nuclear power plants. And here what you see is CSP, which is concentrated solar power. This is a technology that is, proposed and increasingly championed in many areas that have a lot of solar power available. But what is often not recognized is that it also needs a lot of water. Essentially, concentrated solar power is powering a steam turbine. That's why it is a lot more, it can be built at a larger scale than PV, but in order to run that steam turbine, you need water, and there's a lot more evaporative losses. So that's basically the connection. So yes, you can say you're going for renewable energy, solar power, but then you are setting yourself up for constraints for water, and so on, okay? So this is the reason why there has been a growing concern and growing research and action. So just to give you one more update, 2011, in previous years I was showing you how the energy sector was marking water as a critical thing. 2011, again at the World Economic Forum, where they assessed global risks, they explicitly called out this nexus as an important risk for global development. So essentially water security, food security, underpinned by climate change, and how that impacts energy price volatility. This is a major risk that needs to be better understood. Essentially recognizing that, the demand for water, food, and energy is expected to rise 30 to 50%. Globally over the next 2 decades, and there are economic disparities that incentivize short-term response in production and consumption, right? So you may go for the lowest cost option and then set yourself up with some of these issues. And I think this is really the key thing, that any strategy that focuses on just one part alone without considering the others may set you up for serious unintended consequences, okay? And in the noted, the issues are connected with geopolitical conflict and instability. And this is not just something light that they put in there. This is based on real facts. Many people speculated, there's no proof, but many people did say that part of the reason for the revolution in Egypt and unrest in the Middle East was because of very high food prices. That people basically that year, the price of wheat had gone up and just price of local staples had gone up actually considerably. Food prices were causing a lot of unrest in the Middle East. Similarly, in Pakistan, if there are energy shortages, people will come out on the streets. Similarly, in Jordan, that was happening just a few years ago. So we know that water, energy, and food security is not just something about the environment. It has very serious geopolitical and local political, socio-political implications. So really the grand challenge of our times is to understand some of these questions, that as we try to solve for one problem, how does it impact the others? So looking off the research that has started in this area, you can see that if you sort of look at the number of publications that have emerged in this topic, starting from pretty much zero in 2001, there was really nobody talking about this or looking into these problems, you can see that there has been a steady rise over time. And if you look at the geographical distribution for how some of this research is coming about, most of the researchers are based or focusing on, this is really based on, we're looking at address of researchers here. In the US, Australia is actually a country where the water energy nexus is a big issue also, so they've been doing some work on this. Germany, France, a little bit of India, and then some other countries. But you can notice that most of the developing world is absent here. where some of these problems, I would argue, are perhaps most acute and require perhaps better understanding, because we need to improve how we can provide these resources to the people. So it's just to motivate that we need more understanding, we need to do more research in Pakistan and better understand some of these issues. So I'll start off with a simple example. We all visited the Nestle factory, and in all disclaimer, I had these slides before my before my visit. I think it will serve as hopefully as a good example here. And just to illustrate that when we talk about the water and food nexus, we're not just talking about big nuclear plants, and we're talking about all the way from consumer items and so forth, all the way to large-scale infrastructure, right? So this is a problem that we need to better understand and appreciate. And again, as I said, there's no simple solutions or no one right answer, but we need to understand what the trade-offs are and what the implications are, really. So that's really the motivation. So here's the question that, all over the world, bottled water use has increased. It's not just Pakistan, it's basically a global phenomenon. Same in the US, same in the Middle East, and then all over the country. People are using more and more bottled water, and the question is that, well, how much energy is going into this, okay? So some methods of systems analysis that I've showed to you before basically, allow us to assess some of these questions, and the particular one that I've not gone into detail, and I'll also not go into detail here, but I'm just pointing out that life cycle analysis is a method that people employ to answer these types of questions, right? So when you want to study, what's the energy in some total value chain, people do life cycle analysis. It's a very well-established methodology. People have done all kinds of studies ranging from, infrastructure to water bottles. There are limitations as well, which I'll point out in the end, but just to make you aware that this is a set of tools and methods that have been developed to address some of these types of questions, okay? So an LCA essentially is a process in which you evaluate the environmental burdens associated with a product or a process. You assess the impact, of the things that you are evaluating, and then you identify and evaluate opportunities, basically, okay, of improvement. So energy use in bottled water. So for this particular study, this was done by Peter Glick. He is a researcher, very well known in the water sector, based in the US. He heads the Pacific Institute in California. He's a respected authority, and his work spans, all the way from hydrological, research, all the way to questions related to, some of these questions related to society and water use and so forth. So he conducted this research back in 2009. And I'm just describing what it is that they did, okay? So this is a very focused study focusing on the case for Los Angeles and sort of summarizing what they did in their work. So essentially, they tried to quantify the key energy inputs, and then they applied it to 3 site-specific cases. They looked at local bottled water use in LA, then water bottled in the South Pacific and shipped, cargo shipped to LA. So a lot of water is imported. People think that, water from Fiji must be that much pure and nice. So there's a whole market of, Fiji water in the US. And similarly, a lot of Italian and French and so forth, companies sell all these nice brands. So they looked at, these 3 specific cases in the study that I'll quickly sort of show you and share with you. So the process of, that they included in their analysis in municipal water, you have a source, you convey it to some treatment plant, and then you distribute it to a bottling station, or you may draw upon groundwater, or maybe there may be other sources and so forth, and then you have, water being bottled for distribution onwards, okay? So they looked at these specific segments for the system they were analyzing. They looked at manufacturing of bottles, okay, and this was, I'm just saying that we missed out this process yesterday in the factory. One of our colleagues here was mentioning this is pretty interesting to watch, but we missed out on that. But anyways, it was definitely a fun visit, and I really enjoyed learning all about it. But essentially, in their study, they looked at the manufacturing of the raw materials, the manufacturing of the bottles, the water processing, and then chilling for sale and use. They don't look at some of the downstream issues and so forth. So just to tell you about life cycle analysis, this is one of the weaknesses, okay? Because when you're doing the life cycle analysis, it's really up to the analyst on which segment they pick. The segments may not be completely and rigorously defined. There's a lot of uncertainties, but as long as you are, the more clear you are, the more transparent you are, and the more open you are in terms of specifying your assumptions and so forth, it can be a good study. But it is an inherent limitation that there's a little bit of subjectivity in what you choose to study and not, or what you choose to include or not in your analysis. Okay, so here's some intermediate results. They made, again, here some simplifying assumptions, and they're showing them to us that essentially for looking at the energy related to transportation, this is what they assumed, that if you're transporting the water on a cargo ship on the ocean, this is the megajoules per ton per kilometers, okay, and then similarly for air cargo and so forth, okay. So they make some assumptions about the energy cost of transportation. And the transportation that they modeled in their study was of three types. Local production, so the facility is in LA and distributing. It's basically just being trucked for distribution. If it is coming from Fiji, it's coming on a cargo ship, okay, 8,000 kilometers away from LA. And if it's coming from France, it's a combination of cargo ship and then a heavy truck and then local delivery in LA, okay? So they're just laying out what it is that they included in their analysis. And what they showed here is essentially that if you do go through all of these steps, the manufacturing of the plastic water bottles, the treatment, and so on, cooling, their estimate, again, this is an estimate, right? They're not really measuring anything, they're just sort of making an estimate here. That their estimate rate is anywhere from 5 to 10 megajoules, thermal joules per liter. Okay, so these are joules thermal. If you want to convert electricity, you'll use a factor of 3 roughly. So this is heat energy that they're measuring here, so megajoules per liter. So this is sort of the range that they come up with to inform how much energy. Now, if you compare it with the tap water, this is again the case for Los Angeles, where they're just drawing water from the river. They're not doing any groundwater pumping. So again, this is a very local study. So for their case, it would be 0.005 megajoules per liter for the case of LA. Okay. So this is sort of, the types of, analysis that one can do, and it identifies opportunities for, improvement and so forth. So what they said was essentially that some of the key conclusions was that if you're transporting water over a short distance, then essentially the energy requirements are dominated by the production of the plastic bottles. That makes sense. I mean, that's not surprising, right? Because most of your energy input is actually going in manufacturing the plastic water bottles, okay? But if you're coming from across the oceans, yes?
Amount of energy Nestle used to produce 1 ton of water product. The amount of energy we use today is 50% of what we were using 10 years back. It's a continuous process of reducing energy year in year basis.
Yeah.
Like every year we have a target. Yeah. What we used last year, we have to use for the first year.
So that makes sense, and they've also come to this analysis that most of the energy is going in production of water bottles, so we need to reduce that. So you're validating some of these results. Okay. So basically what they're saying is that if you're using bottled water that has been transported over a long distance, then some of the transportation costs may dominate. And then it's a choice for the consumers and also for the managers, right? So if you're a consumer, do you really want to pick the Fiji water? It's about your, environmental sustainability and your personal choices. But essentially, they're putting this out there to inform, decisions, both at the personal level as well as at other levels, right? And then also, we had this discussion about quality. You can't sum the problem down at just the equation for energy. Why are people using bottled water? Well, it allows for portability. In some cases in the US, it's a lot because of portability, that it's just easy to carry one bottle of water around rather than hunt for taps when you're on the move. But here, it's definitely a quality issue. why a lot of people use bottled water, that they assume that the quality is better. So there are many other things that are going on, but recognizing that what are the energy implications, I think is very important and it can be very useful. Okay. Okay, so this was just a little sort of example to sort of motivate, these questions of water, energy, and I'll come to the food issue as well. And what I'll share with you next is now sort of a more larger scale problem. So now we are going to look at the Indus basin. For this audience, I don't need to emphasize that Pakistan's GDP 20% is derived from agriculture. It's a big sector, and a lot of that agriculture is irrigated agriculture in the country, right? So global irrigated agriculture accounts for about 40% of crop production. It uses about 20% of land, but produces 40% of the output. So it's actually a lot more efficient than rain-fed agriculture. So we can assume that many other regions in the world may also turn to irrigation over time to meet their food needs because it is more productive than rain-fed agriculture. Okay, so this is a problem or an issue that needs to be better understood, not just for Pakistan, but I argue that it's globally relevant, that if we can understand better what's happening here, we can be in a better position to inform the debate and understanding for many other regions that may be shifting to irrigated agriculture over time. So if you look at the map, irrigation map of the world, there it is, bright red spot showing how we compare with the rest of the world in terms of irrigated land as a percentage of area, okay? So this big red spot that you see here represents land in which about 75 to 100% of the area is under irrigation, okay? And you can appreciate how it is in the global context. It's really big. We are really at the end, at the frontier, if you will, of maximizing, irrigation. You see some spots here. This is California, where they do irrigated agriculture here in the Central Valley. A little bit of spots here in northeast China. This is sort of Mekong. A little bit of a spot here for the Nile Delta. But you can appreciate how we compare in scale. So we really are at sort of the global frontier of large-scale, massive irrigation, and we need to understand what's going on here. And I think there are sort of three reasons why this is a critical problem and a very relevant problem for us. Okay, one is that, the human impact. I don't need to tell you the numbers of our population, but of course this is an issue of, water, energy, food security is something that's intimately, connected to human welfare in a large country. And then also, because of the acute shortages that we are now facing, sometimes in the energy sectors, there is a finite possibility of real action because we are hitting the limits of some of these resources, right? And then also, when I wrote this, and then still there are all sorts of, restructuring and planning that's always underway. So there, we're not fully developed yet. We haven't built out all the infrastructure. We haven't built out the entire basin yet. So there's opportunity for boom. I won't go through this in detail. Some of you are probably better positioned to explain this to me than I am to you. So I'll leave it at that, except for pointing out that, this is well known that a lot of the water that's flowing through our canal waterways is seeping into the ground, and the losses are estimated to be anywhere from 40 to 60%. So that's a lot of water that seeps into the ground, and that in turn has led to the groundwater pumping that we will talk about. And some of the, if you look at, so this is data that we plotted of, just canal water diversions over time. This has been provided by, the Punjab Development Statistics. And if you just plot it out, this is just showing you the raw data over a 30-year period. You can appreciate that, in the last 10, 15 years or so, something has been happening. There's been greater variation of the availability, and you can see a slight downward trend. If you just put a trend line there, you'll see a slight decline. It's not significant, but you see it there. What is driving that? Maybe we can have a conversation with Asif later on. He was talking about changes in precipitation, and we are getting low precipitation now than we used to before. So I can offer a few hypotheses, but we haven't tested that. But nonetheless, this is actual data of canal water diversions in Punjab. Okay, and if you look across the seasons, In Rabi, it's slightly downward here. So that's when the winter wheat crop is planted, so which is a staple, right? So it's an important thing, and we argue that this trend has led to this phenomena of groundwater pumping increasing at a massive scale. So in 1995, this is the density of groundwater tube wells in Punjab. How did we plot this? We basically used tube well installation data provided by Punjab Level Statistics, and essentially just used a GIS map district level to plot out these dots. So these dots are not showing specific locations of a particular pump. They're just giving you sort of an average sense. Each dot represents about 500 tube wells. They're just giving you a schematic idea of the distribution of these pumps across the districts, right? So 1995 and 2010, you can see how much the system has expanded, right? So this is a massive system that has grown in size. Okay, if you look at the numbers, they're quite impressive, almost 1 million tube wells. Again, these are all government statistics. So almost 1 million tube wells installed in the province. Starting in the 1970s, you can see how much this has expanded in the country. All right. Another key thing to appreciate is that most of these pumps are operating on diesel. So these are off-grid systems. They're not using the power grid, which has, its own interesting things to consider. But there is a fraction that is running on electricity. Okay, so if you look at the size of this system, and you're just like, wow, what's the level of energy going into this? How much energy is going into the system? So we started, asking or investigating this question. And to give you a sense, it's not just about diesel. As I mentioned, there is a fraction that uses energy, and in particular locations, it's very relevant, the electricity used for. So if you look at, so this is MEPCO, so how, the province is divided among different electricity companies. So for MEPCO, actually, if you look at the amount of electricity sold to industry and agriculture, it's almost the same. So in particular regions, actually, there is a lot of demand for electricity, not just diesel, for the agricultural sector. And if you talk to anybody, they'll tell you it's basically because of groundwater pumping. So, I've had conversations with people in the Ministry of Water and Power in Islamabad. They provided me with this data. So this is, so the industry and agriculture in certain regions are actually rivaling each other. That's the point I'm trying to make. And when we have energy shortages and industrial plants are shutting down and many of the things, factories, so many of them have moved out, we are in direct competition between these two sectors. Okay? All right, so what we did was essentially try to analyze, well, let's quantify this. Let's study the system, let's define the system boundaries, and go through this process. So I'll just quickly show you what we did. I'm not going to dwell on any of these steps, but let's cut to the chase and show you some of the data that we started off with. So we said, well, maybe the data is available. Let's look at the government statistics of how much energy is going into the agricultural sector, and this is what we found. The Energy Yearbook is published every year by the this is the HDIP. This is the not human development. This is the Petroleum Institute. So this is based within the Ministry of Minerals and this is Hydrocarbon Development Institute, not hydropower, hydrocarbon. They're based in Islamabad, and they basically do research on the oil sector and production. But one of the interesting things that they do is that they put out the Energy Yearbook for Pakistan. Have any of you guys seen it or used it before? Okay, it's a very useful publication. I'll show you some of these data sets that I've drawn from, some of these publications that I've used. So if any of you are researchers here or others who are interested, then you can go back and draw from some of these data sets, because I personally have been quite impressed with the amount of information that's available. If you start digging, what you'll find is there's actually a lot more information available than you would imagine, than you would think otherwise, and that is what enabled us to do this study. Okay, so if you do this is what we find in the picture. I just plotted out what was the data available. So from 1980 to 2011, the amount of electricity sold to agriculture and the amount of light diesel oil sold to agriculture. So can somebody tell me why this picture looks strange? Is this something that you would expect to see? If, that's right, why is it decreasing? So here I was showing you the previous chart. Now this data was put out by, this data is in the water handbook, okay, which was published by the Ministry of Water and Power, showing you the diesel wells installed. This is the water sector telling you, how much tube wells there are there. And now here's the energy sector telling you this is the energy sold to agriculture. And you just say, but it's not adding up. I mean, the diesel sales should be going up. So we were like, okay, so that's when we identified there's a problem. There's something missing, so we'll have to do our own bit of modeling and our own calculation to really figure out how much energy is going in there, okay? And not to say that this was wrong. What I'll tell you is what we found was that they were basically, it's a matter of bookkeeping, which I will go into as we go through this. So we said, okay, we'll just do our own bottom-up estimation. We're going to look at all the different elements that are using energy, and the different types of fuels for on-farm operations. So we're going to look at field operations, so these are your tractors and machinery that you're operating, and we're going to look at water pumping. So these are two main sources using energy at the farm level, okay? Now, what are the different elements? There you have tractors of different horsepowers, you have tube wells, and tube wells we found three different types of fuel or energy sources. You have light diesel oil, you have electricity, and you have also high-speed diesel, okay? So we said we're going to account for all of that. We did not go into indirect energy use. If you look at a number of studies, people also account for the indirect energy. They look at the energy used for production of fertilizers and then fertilizers. We didn't get into that in this here. So natural gas, and that's another issue actually which Pakistan was very much dealing with, right? So do you send the natural gas for fertilizer production or do you send it to power plants? It's a very relevant issue nonetheless. So what's the difference between HSD and LDO very quickly? So these are just two different types of fuel grades. HSD is used in more high-speed machinery and LDO is just light diesel oil. It's run on types of machinery that are not operating at higher speeds. That's really two different grades of fuel. So we essentially looked at the agricultural machinery census. Has anybody used this census data? It is remarkably detailed. It is, when I opened the document, I was just like, wow, the level of detail that they capture is like amazing. So I'll just show it to you. This is a 600-page document, which the Punjab government puts out every 10 years. They do this census for every district, anything that you can imagine related to machinery, the make, the power, the amount of duration it's operated. It's quite incredibly detailed from what I had not expected. So just to give you a sense, there are 600 pages, and they basically, just to give you a sense, right, they'll tell you in the whole of province, the number of tractors that are present, at district level, who owns it, whether it's individually owned or owned by a number of people, the make of the tractor, right, the horsepower, and then it just goes through the whole set, tractors, combines, water pumps, everything, okay? So this was the basis for getting two key data points for 1994 and 2004, because they do it every 10 years. And I've tried to look for the more recent one. I don't know if they've done another one since 2004, because technically there should be one in 2014 or 15. I don't know, but anyways, so this is done and this data is available, okay? It's publicly available. So we use that, and then the Punjab Development Statistics publish yearly counts of tractors deployed in tubers. So you have the yearly data as well. But that doesn't give you the key data of the operating duration and so forth. So you have to make a little bit of interpolation, which is what we did. So we used a combination of actual census data at a year-wise basis and 10-year basis. The 10-year data was more detailed, which we used as a basis for filling in some of the gaps for the yearly ones, okay? So we used all that data, we made some assumptions about average fuel consumption and so forth. The utilization rate, again, we got the census data, how long they're operating these things for. And then, just to check whether what we're getting makes sense or not, for the LDO case, right? So the number of machinery that was running on the low-speed machinery, the LDO tube wells, we had data for actual LDO sales for the agriculture that I showed you earlier. So this is how our estimate compares with the actual data. And you can see that it's actually fairly decent. So this is our estimate based on our calculations. And this is basically the actual sales reported in the HDAIP book, okay? So we said, okay, so at least our LDO component is well modeled, where we're getting a decent estimate. But what about the rest? For the rest to cross-check, we used results, and these were just results, so there weren't any details behind this, but there were results available by PAC-IEM. PAC-IEM is a Pakistan Integrated Energy Model. This was commissioned and developed for the energy wing of the Planning Commission in Islamabad, in which they essentially converted Markel, which is an energy planning model, for the Pakistani context, and they ran various scenarios. And they published one or two reports that are available in which you can sort of look at some of the key results that they found. In those reports, you can see some of their estimates that the model was producing, in which I was able to find that there is an estimate of the energy use in the agricultural sector, estimate for Punjab, in which they were estimating, for electricity, LDO, and HSD. These are the estimates that we got for our study. Okay, so this is pretty much similar. Okay, sorry, these are the data for our study. So PAC-IEM and the MIT study. Okay, so so what you can see is that for LDO and HSD, we are actually fairly close. Okay, we're actually fairly close. So LDO is this H. So they had an estimate of 2.7. We were estimating 2.4. So we were in the ballpark. Okay, we were in the ballpark. So here's the breakdown for what we found. What we see is essentially that over time, and I'm just showing you data for the last 10 years because we didn't want to interpolate too much back. So since the data was 1994, so we started, and then you can see basically this. This whole thing is missing in the estimates right now. Only LDO electricity is accounted for when you open up the energy yearbook, and this is the most significant piece. Now, I have some hypotheses as to why we see this sudden jump in the data, right? If you look at the number of tube wells that were installed, there's a big jump in those years. And they correlate well with years of drought, when there was actually a lot of water shortages going on. So essentially, the uncertainty in the water supply and years of drought basically get to this dynamic where more people install pumps, and then now when you have the pumps installed, you're expanding your base. So essentially, it's the uncertainty and the years of drought that drive to the increase in size of the system. Okay. So what's the big deal? Okay, we've quantified it and we've run the numbers. So what, right? I'm always asking the so what question. So great, we did the analysis. So now what do we do with it? And why does it matter? Well, I would argue the one important thing that emerged, which is that if you actually look at the officially reported statistics, this is a breakdown that's given for the different sectors for energy use in the economy. So if you look at, for the case of Punjab, these are the reported statistics in which agriculture is shown to have just a 3% share, which would also should raise flags because it is the biggest sector in the province. So how come it's only using 3% of the energy share? But this is what you find, okay? But if you account for the different calculations that we did in which we tried to adjust for the HSD use, the high-speed diesel use, our estimate is that it's 20%. Okay, and how are we getting to this? What we're doing is that we're essentially taking away from the transport sector and putting it into the agriculture sector. And why we're doing it is because that in the energy yearbook, they basically state that HSD is accounted in transportation. Even HSD used for tractors in agriculture is accounted for in transportation. So it's not that, it's basically bookkeeping, as I said. So they're just accounting for it differently. But my argument is that if you don't fully reflect, the real reality, you're going to impede optimal planning and policy making. Okay, so that's really the key take. Again, I just want to highlight that these are our estimates. We haven't gone into the field and measured or done anything of that sort. But these estimates are based on government statistics, and we argue that I would argue that at least this makes more sense given the scale of the system and the way it has expanded, and some of the trends that you see reported for agriculture don't make sense.
And probably it's also because point of sale was
Yeah.
same to one farmer buying something for the seller. It's impossible to know whether they're
I agree. There's probably a difficulty in the system that how do you keep track of the usage? Yeah, but this is, they're keeping track of the fuel sales, right? So they of course, they're tracking HSD, they're tracking LDO, but they lump all the HSD in transportation. And this is again highlights maybe a need that what you're pointing out. Maybe we need some better mechanism to report data better and so forth.
Transportation used to carry the goods from the farm back
Yeah,
to the market.
yeah,
So,
yeah.
that is the 5 years.
Yeah, yeah. But my main point is that if you basically have a better sense for the water one, which is what we're making here, because a lot of this HSD is actually going into pumping. And what we found out, and that was through the census actually, because in the census reports, what you find is that in the early years, the majority of the tube wells were running on LDO, and that's what gets captured. But then in the latest one, it had completely shifted. So 80% of the tube wells were using HSD. And that is why we said that all this groundwater pumping is just not being accounted properly because all the HSD gets lumped into transportation, and that is a severe sort of lack, I think that should be fixed. So again, these are just our estimates based on census data, based on just calculations, but we argue that it is a lot more than 3%. And something, hopefully can be done. But also recognizing that, here are the opportunities for improvement. All right. So we were having a discussion about solar groundwater pumping and other types of solutions that might be out there. Because if you have a fuel that can be used for other types of applications, then the question is open because you can't run cars on solar power, at least not yet. You can't run many other systems, but you might be able to run groundwater pumps on solar power. And those are the types of things that one can now evaluate. If the government wants to evaluate, subsidies for solar power pumping, or want to incentivize maybe research in solar power, here now you can really make quantitative estimates that this is the amount of benefit we can expect, or this is the amount that is at stake. So that's really the power of quantitatively modeling and getting an estimate of what the system is doing. Just to sort of put a context of this wider issue and why it's important, what we did was we looked at total crop production from Punjab over this period of time, just to get a very gross estimate of the energy use and food production or agricultural production, I should say, in the province over this period of time. And what we find is that the direct energy intensity has increased 80%. So for producing the same kilogram, we're using 1.8 megajoules now versus we were using 1 before. And that is, again, because of increased pumping.